Hello and welcome. Today we are looking at household electricity, and this is for your Physics Unit 2 GCSE. Now we're looking at electric current, and we can break that down into two kinds. We've got direct current, which is sometimes written as DC, and we've got alternating current, sometimes written as AC. And with direct current, we are usually talking about anything that runs off a battery, so maybe your mobile phone, a torch, a laptop. Anything that runs off a battery is likely to be running off direct current. Alternating current, on the other hand, is the kind of current that is supplied by the main socket in your house. An alternating current is one that repeatedly reverses direction. So that means it flows one way and then the opposite way in cycles. And the number of cycles that we have per second is called the frequency. And in the UK, the frequency, or the number of cycles per second, is 50. And we say 50 hertz. Hertz just means cycles per second. And while we're here, we can look at the voltage as well, the potential difference. The voltage supplied by our mains is 230 volts. Okay, two important bits of information that you need to remember. So the frequency of 50 hertz, voltage of 230 volts, and an alternating current supplied by your mains electricity. Now let's have a look at a couple of graphs. Circuits that we could use to look at alternating and direct current a bit more. I've got a circuit set over here with a battery, and that's our direct current circuit, and we could measure what we call the potential difference, which we've looked at in previous videos. We can measure the potential difference or voltage across a component. Here is just a fixed resistor. We can measure it with a voltmeter, but we can also use this thing called an oscilloscope. So in position X here, I've got an oscilloscope, and the same for the circuit that's running not from direct current but from alternating current. And this oscilloscope is basically a machine that looks a little something like this. This is a very bad diagram of one, but it's basically a machine that has a screen where you can take a reading, a bit like a graph, and you can see a little bit of what's going on in terms of the potential difference in the circuit, and therefore what's happening with the current. So let's have a look at a couple of those readings that we might get. Here is our potential difference versus time for the circuit, our direct current circuit. So if we were to look at the reading that we got, this green line shows how the potential difference is changing over time. And in actual fact, you can see it's not changing. It's stuck there steady at this level here. What is that level there? Well, we can work it out by using this key here. 1 square equals 4 volts. So if we look at the number of squares, 1, 2, 3, 4, 5, we've got 5 squares. So this is showing a steady reading of 20 volts. Now that 20 volts is for our direct current. So that 20 volts will be supplying a direct current, a current going in one direction, related to this 20 volts. Now what about if we have alternating current? Well, that display will look slightly different. Because the current is alternating, that is caused by a potential difference that's alternating, or that's constantly switching, and therefore you will see a graph reading or a trace that looks a bit like this. So it will go first in one direction and then the opposite direction, and it will keep switching in cycles. And we can work out the potential difference here. You can see it changes constantly throughout the graph, but we measure at the peak. Okay, so the peak is there, and we can read that off the graph. And here I've got a slightly different key. I've got 1 square is 50 volts. So if I've got 1, 2, 3, 4 squares there, I've got a reading here, a peak reading of 4 times 50, which is 200 volts of potential difference. Now that doesn't necessarily mean that the overall supply here is going to be 200, but the peak here is actually 200 volts, and that's how you would read it off that graph. Okay, so there's some information about alternating and direct current. The next thing we're going to deal with is actually for the higher paper, and we're going to work out how we can calculate the frequency based on these types of graphs that you might get off an oscilloscope. Now the first thing to remember is this keyword here. The keyword is period, and that means the time taken for one cycle. So one cycle shown on here, if you measure the time that took, that would be called a period. Now quite straightforward for this one. I've got the graph here and time along the x-axis here, and I've given it in seconds. So we've got 0.02, 0.04. So one cycle is actually from this point here all the way up down again, and back to the middle again. So that's one cycle there, and the time taken, as you can see, is 0.04 seconds. So a period, or the period for this particular readout, is 0.004 seconds. That's the time taken for one complete cycle. Now from this you can actually work out what the frequency is. Now the frequency, remember, is measured in hertz, and that means how many cycles per second. So if I've got one cycle and that takes 0.004 seconds, how would I work out how many cycles I have in 1 second? Well, it's a fairly straightforward calculation. You just say 1 divided by 0.004, because we're looking at seeing how many of these 0.004s go into that 1 second. So that's the calculation we do, 1 divided by 0.004, and I believe the answer to that is 250. So the frequency for this particular readout is 250 cycles per second, 250 hertz, and that's how you would do a calculation like that. Now I think it's probably worth practicing one or two, so I've got one fairly straightforward question and one that's slightly more difficult, but let's have a look at the slightly easier one first. Now remember, the period is the time taken for one cycle, so let's have a look at this question. We've got this new word thrown in here called the time base. I haven't given you any readings on the x-axis, the time axis here, so how are we going to work out the time taken for one cycle? Well, we can use this thing called the time base, and that tells us that the readout gives us 0.001 second per division. So every division we have here is 0.001 seconds. So if we measure on our graph here, we've got 1, 2, 3, 4. So for the first point at which it crosses the graph is 0.04, but that's not what we want. We want one complete cycle, and that goes from here to here, that point there. So that would be 1, 2, 3, 4, 5, 6, 7, 8 squares, or 8 divisions, and remember each division is 0.01, so the period would be 0.008 seconds. So that means one cycle takes that much time. Now how do we work out the frequency? Well, again, it's 1 divided by the period, which is 0.008, and that gives us an answer, I believe, of 125 hertz. Remember to get the units right on both of these calculations. So the frequency for this one is 125 hertz. Now for the last one, might be worth having a go yourself. It says the time base is 0.005 seconds per division. Calculate the frequency. So you might want to pause here, have a look at seeing if you can work that out, and in a moment I'll go through the answer, so you can have a go now. Right, so how do we do this question? Similar to what we've done before, we've got a time base of 0.05 seconds per division. So let's have a look. We've got 1, 2, 3 divisions up to half a cycle, but we don't want half a cycle, we want the whole cycle. So it's 1, 2, 3, 4, 5, 6. So we've got 6 divisions. 6 times 0.005 will give us 0.03. So the period is 0.003 seconds. Remember to put the units in, and the frequency therefore is 1 over 0.03, and I believe that is 33.3 hertz. That's a 3 recurring. 33.3 hertz. So that's how you work out the frequency. Incidentally, this is not a formula that's given in the exam. Remember, this is for the higher tier. You should be able to work out that if one cycle takes 0.03 seconds, how many would you get in 1 second? And it's straightforward how you do it. It's just you just do it like that. But this is not a formula that you'll be given in the exam. Okay, so that's basically alternating and direct current, some higher tier calculation stuff for working out frequency. That's me done for this video, and I'll see you again soon.